Okay, so I'm not going to talk any longer. A warm applause for Will Happer.
Well, thank you very much, Marcel, for that kind and exaggerated introduction, but I appreciate it. So I'm going to try and keep this at a non-technical level. Every now and then I may put in something that's a little bit too technical than it should be, but I'll try to avoid that. And so first let me say that all of us here, I think, are real environmentalists. We want to live in a clean environment. We want not to make it worse. We'd like to make it better. And so this is what we don't want. This is Shanghai. My son taught in the American school in Shanghai, China for 8 years, so I saw a lot of Shanghai, visiting my grandchildren there. And it often looks like this. And this, by the way, is not CO2. If you can see it, it's not CO2. You know, this is a combination of coal smoke and burning last year's wheat fields, you know, to get rid of the pests before you plant next year's crop. But it's not a good thing to be living in. And so I'm against that, and I know you're all against that as well. But CO2 is not a pollutant, so let me just compare what we breathe out. You know, each of us breathes out about 2 pounds of CO2 a day. That's almost a kilogram a day from each of us. You know, there are 8 billion people in the world, so that's 8 billion times a kilogram a day. That's a lot of CO2 just from people living. And one of the things that worries me when I hear fanatics talking, they say, well, the root cause of our problem is not CO2, it's too many people. You know, we shouldn't have more than 1 billion and probably less. And so I look around, there are 8 of us in the room, and which 7 of us is supposed to leave the earth, you know, to please the Greens. So I never got a good answer to that question. And anyway, look, when you burn a carbon-based fuel, you make a lot of CO2, a fair amount of water, more if you're burning natural gas than if you're burning coal. There's a little oxygen left in the smokestack, and essentially all of the nitrogen. There's a little bit of nitric oxide made, and that's a pollutant that you have to get rid of. And so plants should be designed to make sure that these are the only things that come out of the stack. But that's not that different from our own breath. You know, we breathe out almost the same amount of water as a coal plant. We breathe out somewhat less CO2 and a lot more oxygen. But there's fundamentally not a lot of difference. We're both systems that are based on burning fossil fuels. In our case, it's carbohydrates and fats. In the case of power plants, it's fossil fuels. This is my wife, Barbara, and this is what's happening in New Jersey. I'm sad to see it's happening in Holland, too, but once green fields are being devoured by these black solar panels, there are more and more of them. This is a recently built one, but the older ones are full of weeds, and they don't work very well, and it's a complete waste of land and a waste of money. So why this is a good thing, I don't know. People seem to have forgotten that, you know, when the sun goes down, these things don't work. They don't work today in Holland because it was cloudy all day. So it's the dumbest thing I can imagine. So what we're facing now is actually not so different from the medieval Crusades. And you remember the Crusade motto was Deus vult, God wants it. And the rationale for the crusade against CO2 is very similar. It's almost a religious thing. People believe in it. Do you they ask you, do you believe in climate change? What does belief have to do with it? It has to do with what are the facts. Is climate change a problem? The answer is no, it's not a problem at all. And CO2 is not a problem at all. But it's difficult for us who have a scientific or technical background to have a successful debate with people who are moved by emotion and religious devotion to planet Earth, Mother Earth. And I'm not sure how to solve that. I'm not sure there is a solution. Well, here's another example of the green energy future we're facing. This was one of the first wind farms, so-called farms. It's nothing but junk now in California. These things wear out. Nobody knows what to do with them when they wear out or where to dispose of them. And again, they don't work very well. They stop turning when the wind stops blowing. All right, well, now let's turn to something that's a little more pleasant to discuss, and this is the realities of how the Earth's climate works. So Earth is heated by the sun, and I think you know that averaged over a year, most of the sunlight falls on the equator or near the equator, although the maximum per day is at midsummer in the North Pole. Actually, the North Pole gets more sunshine at midsummer than the equator ever does, averaged over 24 hours. But averaged over a year, the equator wins because it's dark all winter up here. And the sun energy has to go somewhere, and close to the Earth, most of the solar energy is carried upward by convection, especially moist convection, moisture from the oceans, moisture from the wet forest, goes up carrying enormous amounts of latent heat. It's basically steam heating the upper atmosphere. And these upward drafts of energy at the equator go to enormous heights, nearly 20 kilometers. So that's the height of the tropopause near the equator. It's much lower here where we are in Holland or over here. Here it's maybe 10 kilometers or even less. And but sooner or later, you run out of air to carry energy away from the Earth, the energy the sun has put there. And so at the top of these convection cells, energy continues out into space as radiation. So Earth cools itself from the solar heating in this complicated mixture of convection and radiation. And the radiation that is necessary to finally get the energy out of there to get rid of the heat is released from all altitudes, from the surface, from halfway up this convection cell, and from the very tops of the clouds. So that's one of the reasons it's a little tricky to calculate anything with any degree of reliability. No one would know better than a Dutch audience about the trade winds, because Holland was based on using the trade winds for many centuries, from Indonesia back to Europe and back the other way. And so as this air comes up near the equator, it has to suck air near the surface downward, and so the air is deflected eastward. And those are the winds that you use to sail back from Indonesia. And where the air falls down and goes up to the north, it's deflected to the west. And so those are the return paths back to Holland. So it's a lot easier to go to Holland from North America than it is to come up from Africa, because you have these prevailing westerly winds, which are driven by this falling air that came from the equator. So it's very, very interesting science. It's really tragic that has been corrupted by all sorts of political forces, because this is interesting stuff, it's important stuff, but it's no longer real science. It's some, I tell my friends, it's some combination between a religious cult and organized crime. So, all right, So here in a cartoon is what I tried to say. By the way, I hope I'm not being too fast. I know I'm not speaking in Dutch. I apologize, but I will try to be clear. So the sun heats us. We only get about half of the heat from the sun because the rest is reflected by clouds. And when the real truth of climate is finally understood, and I'm sure it will be, but it'll probably take another 50 to 100 years, I'm almost certain that it will be clouds that are the dominant factor in controlling Earth's climate. That's already becoming clearer and clearer that the models are not working, and probably because of the poor treatment of clouds. Anyway, the clouds reflect about half the sunlight. They're a little reflected from the surface. And then that heat goes back. It starts out, as I mentioned, largely as convection, rising moist air. The air condenses, releases lots of latent heat, and is converted then into a flux of radiation, long-wave thermal radiation, the type that you and I emit. In America, we have rattlesnakes, and they can sense the thermal radiation, so they strike where there's something warm and, hopefully a rat or a mouse that they can eat rather than something dangerous. Okay, but anyway, they use the same thermal radiation for living. So we're going to talk a little more about this later, but this is what ultimately cools the Earth. And this radiation that's released to space is affected by greenhouse gases. And so we'll say a little more about greenhouse gases in a minute, but roughly speaking, a greenhouse gas is a gas that's transparent to sunlight, so the sunlight can go right through carbon dioxide. It can go right through methane and hit the surface if there are no clouds in the way. But it is hindered from escaping to space. So these greenhouse gases are free pass for radiation from the sun, but they obstruct radiation going back to space. So they hinder the radiation. It means that the surface has to warm up a little bit to make up for that, and that's where the greenhouse warming comes from. So there is a greenhouse effect. There's no question about that, and you see that from satellites as it's absolutely clear, and that's been known for a long time. So now let's talk about what these greenhouse molecules are. By far the most important is water vapor. And I watched closely at the Glasgow conference, and so far they haven't banned water vapor, but but they may. I hate to mention it. You never know what they'll do. The second most important greenhouse gas is CO2. But it's considerably less effective than water. It's maybe a third as effective as water vapor. And if you include clouds, then water vapor is 95% of the greenhouse effect. But vapor alone is only about 3 times CO2. Then very minor are methane, which the fanatics are using to beat up on the poor farmers who are making an honest living the way they have for centuries. All of a sudden, they're a threat to planet Earth. And nitrous oxide, which is also a product of the farming industry, use of fertilizer. These are very minor. Their effects are about the same, so I'll mostly focus on methane, but when I talk about methane later, you can imagine that nitrous oxide is about the same. So the way these molecules intercept radiation is that they can vibrate and rotate. And all of them, when they vibrate and rotate, produce oscillating charges. And if there are probably some electrical engineers and physicists who in the audience, and they know that when a charge oscillates, especially a pair of charges, a plus and minus, when they oscillate, they can absorb or emit radiation. And the oscillations and rotations of these things are very, very complicated. And that's what you have to take into account when you're looking at radiation transfer through the atmosphere to outer space. So here is where some of the absorption of these gases takes place. This is, I think, a well-known picture to many of the audience. And so here's water vapor. I said water vapor dominates the greenhouse effect. And you can see here that the absorption of water from here to here, that's 100% absorption of light trying to go from the ground to outer space. So there's a little window here where radiation can escape from the ground and get directly to outer space. And then there's some nice windows in the visible. So sunlight gets through water vapor over here. This is where sun comes in. Water's almost transparent, but water's quite opaque in the region of frequencies that the Earth emits. So I should back off a minute and say what's plotted here. What's plotted here from left to right is the wavelength of radiation. So visible radiation is about a half a micrometer. So this is 10 to the minus 6 meters, a millionth of a meter, and visible light is in this region, around a half. And thermal radiation is more like 10 to 20. So it's in this region here. So this is much longer wavelength radiation. It interacts in different ways with molecules and tends to be absorbed by these greenhouse gases. Here you can see carbon dioxide already, even on this chart, doesn't look very impressive compared to water, and it's not. Methane is even less impressive. Here's methane. Nitrous oxide, also very puny, and it interferes with both water and methane, so it's not as effective as you might think. And it has another absorption here that interferes with carbon dioxide. We'll see some of that in more detail. So plotted on the top here are some smooth curves, and these are the famous Planck curves, and these are the curves that gave birth to quantum mechanics. And people tend to forget that quantum mechanics actually was invented to try and explain these observations here, because until Planck came along, people knew how to calculate this side of the curve. They knew that radiation should fall off like this as you go to longer wavelength. But all the calculations showed that as you went in this way, the radiation intensity would go up and up without limit, like Al Gore's pictures of global warming. And this was clearly wrong, but, the calculations were 100% correct if you assume classical mechanics. So this is what brought on quantum mechanics, the idea that energy is not emitted in any amount you like, but it's quantized. There's a minimum amount of energy that the molecule or the atom has to emit, the quantum of energy. So there's a wonderful story that goes with the physics associated with radiation. And these Planck curves depend on temperature. So the sun is very hot. It's nearly 6,000 degrees Kelvin or centigrade. It doesn't matter with such a large number. And for the Earth, though, the Earth is much cooler. It's 20 times cooler than the sun. And so these are different possible temperatures of the Earth. This is relatively hot. 310 Kelvin might be the Sahara Desert, and 210 might be the ice sheet over Antarctica. And the middle one is about where we live most of the time, the blue one. But they shift from left to right as the temperature of the Earth goes up and down. Now, greenhouse gases were discovered by Anglo-Irish physicist John Tyndall, and he was delighted to have discovered these things. They were brilliant experiments that he did, but he was very grateful for greenhouse gases. He thought they were really good. He thought we should have more greenhouse gases, more carbon dioxide, more water vapor. And here is his comment about the most important one, and he recognized water was the most important one. So I'll read it to you. Aqueous vapor is a blanket more necessary to the vegetable life of England than clothing is to man. Remove for a single summer night the aqueous vapor from the air, which overspreads this country, and you would assuredly destroy every plant capable of being destroyed by a freezing temperature. The warmth of our fields and gardens would pour itself unrequited into space, and the sun would rise upon an island held fast in the iron grip of frost. Boy, only an Irishman could use the English language that way. It's really good. I wish I could talk that way. So, and everyone who studied greenhouse gases since, perhaps the most famous successor was Svante Arrhenius, a Swede, and Arrhenius was convinced that more CO2 was good for the Earth, especially for Sweden, where it's a little too cold. If you add a few weeks of growing season, it makes a huge economic impact at the latitude of Sweden or Norway or northern Russia. It doesn't matter much further south, but it helps there too. So, okay, let's come back to hysteria. So the hysteria is this curve. And so this is year, starting in 2008 approximately, and up to just a year or two ago. I'm sorry, I don't have it dated, but this is continuing to go up. We're at about 420, I think, parts per million now. I don't know what the latest is. But CO2 is steadily rising, and this appears to be mostly due to burning fossil fuels. It's argued, I have an open mind, it may not be, but that's the most logical explanation. So let's look at this in a minute. You notice that the red curve is the month-by-month measurements of CO2 at Mauna Loa in the Hawaiian Islands. It's up on top of a volcanic mountain where there is CO2 emitted by the volcano, but I think they've taken that into account. Okay, I've looked at the data and I'm satisfied it's okay. But you notice that during the winter months, the CO2 levels go up quite a bit. And every spring and summer, they fall. They go up and down, up and down. Also, if you look closely, this oscillation, it's more clear if you go further. It's getting bigger with time. So what you're looking at in this oscillation is the growth of plants. So when summer starts in the northern hemisphere, and Hawaii is a little bit north, it's about 20 degrees north of the equator. So it sees all of the air that's come from Asia and North America that's mixed up overhead. Summer comes and plants suck out CO2 very rapidly from the air until the end of summertime when the sun moves south and the plants no longer grow in the north. And so all winter, respiration continues, the fungus continues to grow in the soil, and so CO2 levels are going up just from the presence of life. Then next summer comes down, they fall again, up, down. But the downs and ups are getting bigger and bigger. That's because the earth is getting greener. There are more plants every year, everywhere on earth. And why has that happened? It's because of more CO2. Plants have been starved for CO2 now for several millions of years, and they're finally beginning to breathe more easily. And CO2 levels are far, far below the optimum, which is probably 1,500 or 2,000 parts per million. There isn't enough oil and coal to produce that much CO2, but anyway, that would be the ideal as far as plants are concerned. It would hardly matter to us in terms of the Earth's temperature. Anyway, this is the basis of the concern that CO2 is clearly going up, and it's going to continue, who knows, probably another century. It will probably begin to bend over as we use less fossil fuels, but it's going to continue. And so supposedly, because of the greenhouse effect, which I mentioned, which slows the cooling of the Earth, this will continue to slow the cooling so much that we'll all boil to death, at least Greta Thunberg seems to think that. So, and who am I to argue with her? So let me show you what really happens. Okay, you can calculate this very reliably, and you can compare calculations with what satellites observe. And so, what I'm going to show you is absolutely rock solid science, rock solid physics, and even the zealots in the IPCC, at least those who know some physics, don't disagree. So this is not controversial. So here is the the most important graph that I hope that you will remember. So now what I've plotted here is another Planck curve. You remember the curve that gave birth to quantum mechanics, and there's Max Planck. Max Planck was one of my heroes. He invented quantum mechanics, and he was one of the few German scientists who remained in Germany during the Nazi period, did his best to be an honest, decent man. His son was hung by the Nazis for being involved in a plot to assassinate Hitler, so he paid a very heavy price in many ways for being a good man and raising good children. Besides which, he was a great physicist. You know, the quantum revolution is due to this man. But anyway, what you actually see if you look down from a satellite is not this type of radiation coming up from the Earth. So here again is the frequency of the radiation. I've switched now from wavelength to frequency. And for thermal radiation, you measure frequency as the number of waves per centimeter. So this means that there's radiation that there are 100 wave wiggles for every centimeter, if you could imagine taking a snapshot of the wave. So these are called, so it's called wave numbers or inverse centimeters, but it's a spatial frequency. And what you actually observe looking down from satellites is something very close to these black curves that I'm showing here. So they look vaguely like the Planck curve, but they're very jagged and messy compared to this beautiful smooth curve that Planck discovered. And this jagged curve, the theory of this came soon after Planck, and it was due to Karl Schwarzschild, who was another hero of mine. He was another German physicist, and he is probably best known not for this curve, although it's very important, but the first person to solve analytically Einstein's equations of general relativity. So he's a very prominent figure in cosmology. You notice he died in 1916. He died on the Russian front in World War I, not because the Russians shot him, but he had some horrible autoimmune disease that finally caught up with him as he was in the poor, living conditions there on the Eastern Front. But goodness knows what he would have accomplished if he had lived a little bit longer. But the black curve is the Schwarzschild curve, which takes greenhouse gases into effect. And the smooth curve is Planck's ideal curve, which would be true if there were no greenhouse gases. So if the Earth had no water vapor, it had no CO2, ozone, methane, nitrous oxide, you'd have the blue curve, and the real Earth has the black curve. And the black curve is very close to what you actually observe. Now, you notice here I've now plotted a red curve, which is what happens if you take 400 parts per million of CO2 and double it to 800 parts per million. So the effect of doubling CO2, 100% increase, is to go from this black curve to the red curve. The red and the black are identical over most of the spectrum. And here they differ by about 1%. So you've got to fix that in your head. When people talk about the horrors of increasing CO2, even if you double CO2, we're a long way from doubling CO2. The only difference is this tiny difference between the black and the red curves. IPCC does not dispute this. They don't dispute this. And what gets them very angry at me is showing this picture, because they say, no, you should never show that. It'll give the public the wrong impression. You should show the area on the curve. This is 274 under the red curve. It's 277 under this. And so the difference is 3. You should only show 3, and suppress this area here, this baseline. So, but they will not dispute this curve. And so that's the facts. That's the facts about CO2. It's a tiny effect. It's about a 1% change if you double CO2. 1% change of the cooling radiation to space. That's easy to make up with about a degree of warming of the surface. So when people ask me what is the most probable warming, well, if nothing else changes, this 1% change in radiation to space will make about a 1 degree upward change in the temperature of the surface. So I'll come back to this in a minute, and this is very discouraging for the alarmists. And so the way they get Is it okay? Okay again? Yeah. Thank you. They have invented all sorts of feedback mechanisms that will amplify this small direct effect of CO. All of them involve water in one way or another, either the water vapor, which you could see here, or clouds. Now, there are many greenhouse gases marked here. This is where CO2 works. And by the way, if you take all the CO2 away, you get this green curve. So look at the difference. The first 400 causes this change in radiation to space, a huge change. The next 400, almost no change at all. And so the technical jargon for that is that the CO2 band is saturated. You've reached the point of diminishing returns. The first 400 parts per million had a big effect, the difference between green and black. But the next 400 has almost no effect. And I'll try and explain how that happens later. But the same thing happens with other gases. Here's a little more CO2 at this corner here. But here's methane, and I'll show you the similar curve for methane in just a minute. But key message is that CO2 is a very poor greenhouse gas now. You can double it, it almost doesn't matter. Okay, and so you have to be very inventive to somehow turn that into a scary story. And they've been invented, believe you me. Okay. Now let's turn to methane. I promised Marcel that I would say something about methane, because methane is being used to abuse poor farmers who are making an honest living or serving us all, allowing us to have adequate diets. I can't say how much I respect good farmers. But green methane is said to be a super greenhouse gas, and again, it's a lie. It's not true. But let me tell you what the facts are so you will understand them and be able to carry on a conversation with somebody who doesn't know what they're talking about, which is most of them. Okay? So it is true today that every additional methane molecule, methane is CH4. I think I showed a picture of methane. Let's go look at it again. Yeah. So here's methane. It's this beautiful tetrahedral molecule. It's kind of hard to draw, but if you want to draw it for your friends, the first thing you do is say, draw a cube, and then you put hydrogen atoms on the corners of the cube and imagine the carbon in the center of the cube, and then that gives the right tetrahedral structure. My drawing abilities aren't very good. I'm certainly no Escher, but that's methane. And methane oscillates and absorbs radiation in the process. So it's true that each additional methane is 30 times more effective in hindering the escape of radiation to space than a CO2 molecule. So on a per molecule basis, methane is 30 times more effective. Some say 20, some say 50, but 30 is pretty close to the right answer. And here's the thing that they don't tell you, and that is that CO2 concentrations are increasing 300 times faster than methane concentrations. There's very little methane in the air. You measure methane in parts per billion, and you measure CO2 in parts per million, a factor of 1,000 difference. And so you have to take this factor of 30 and divide by 300 the rates of increases. So the contribution of methane is about 10% that of CO2. And I already mentioned that CO2 itself has a very small warming effect. So, if you double CO2, you get about 1 degree. If you double methane, you might get 1/10 of a degree. So it is, and for this, you're bankrupting the farming sector. It's absolutely insane. but there's a lot of, world has always had a lot of insane people. So here's the rate of increase of methane. You notice it also has the winter-summer cycles, just like CO2. It goes back a little longer. This starts in 1988, soon after we had satellites operating, but I believe this is maybe also from Mauna Loa. Yeah, from Mauna Loa. But the scale here is in parts per billion, not parts per million. And also you notice it's not nearly as steady. So most people believe that this pause here from 1996 to about 2004, this is when the Soviet Union broke up. And the Soviet gas pipelines were a disgrace. You know, they leaked all over the place, so they were pouring methane into the atmosphere. And so they were privatized, and the private companies realized this methane being wasted was worth a lot of money. You could sell it to the Germans or someone else, and so they fixed the pipes. And so as the pipes got better and better, you know, there was less and less methane released, and so there was a long period where there was no increase. And so that was the collapse of the Soviet Union. You can see it here in the methane. And well, they finally got it fixed, and now methane is going up again, but very slowly, as I say, about 300 times more slowly than CO2. And nobody is quite sure what it will do, but if it continues at this rate, it's simply not a problem. It's not ever going to be a problem. And here's a similar curve for, again, here's the frequency of radiation going out the top of the atmosphere. The black curve is the Schwarzschild curve, what actually goes out. The blue is the ideal Planck curve. And here is methane, and the red is double methane, the black is current methane, and the green is take all the methane away. Okay, and it's nothing. It's really nothing. It's a 0.1% effect if you double methane. It will take us forever to double methane, a century to double methane. So again, they don't tell you this. They say methane is 30 times more potent than CO2, and so you have to remember to supply all the caveats that go with that. All right. Let's see here. So here is actually the warming that one would predict. So if you take the worst possible IPCC projection, and I think this is off by a factor of 3, but nevertheless, the warming from CO2 in 50 years would be about 10 times that from CH4. This is assuming 3 degrees for doubling CO2. The real number is probably closer to 1, and so this curve is 3 times bigger than it should be. But the main point was to show how small methane's contribution was. Now let's talk about the so-called pollutant, CO2. So this is now switching to geology. And so let me just state right out, the Earth has been in a CO2 famine for several tens of millions of years. And this is what I mean. I mean this curve. So here we are today. So this is today. And this is going back in time. This is 100 million years back, 200 million years, 300, 100 million. Our primate ancestors evolved maybe 70, 80 million years ago, when CO2 levels were probably 3 times what they are today. So this is the amount of CO2 compared to today. So today is 1, or pre-industrial is 1. And so we've not yet double pre-industrial, so we're maybe about here now. So we've gone up a little bit, and that's the reason for all the hysteria. But look what the past has been. Most of the past CO2 levels have been 5 times, 10 times, even 20 times higher than they are today. This is very solid, geophysics. It's from Robert Berner at Yale and his colleagues, and very few people contest this. It comes from looking at carbon isotope ratios and paleosols, and looking at fossilized leaves and counting stomata, and there are a number of other proxies that one uses to try to estimate atmospheric CO2. So it's not perfect, but it's certainly not off by factors of 2. And here's what lived. When we evolved, there was a lot more CO2. When the dinosaurs were wiped out by the meteor back here, it was almost 10 times more CO2 than today. The only time it's really been as low as today was the Triassic. This is the Triassic period, 300 million years ago, when all sorts of horrible things were happening. The North Atlantic was opening up again, and my state of New Jersey was attached to Morocco at that time. And it's a long way to Morocco now, but you used to be able to walk from Princeton to Morocco. And here are the coal swamps back here. My friend Patrick Moore, who's the one of the founders of Greenpeace, but now a very staunch ally in opposing climate hysteria, likes to theorize, and he may be right, that this loss of CO2 back at this time was due to the invention of lignin in plants. So, lignified wood doesn't rot very well. And so instead of being immediately decomposed and turned back into CO2, it gets buried to form coal beds. And so after a while, it looked like we were going to run out of CO2 and the life would die out. But it's come back. But we're close to those levels now. In fact, during the last glacial maximum, 20,000 years ago approximately, there's quite good evidence of CO2 starvation all over the world. And one of the things that you don't have to be very sophisticated to understand is if you look at the ice cores from Antarctica, where you measure CO2 in bubbles, you can also measure dust. And the ice was incredibly dusty, at the last glacial maximum. So it must have been that at that time, there were dust storms all the time. And the interpretation is that most of the high plains in Asia, the Gobi Desert, the western U.S., the high plains of Africa were devoid of vegetation because it had starved from not enough CO2. So there were no plants to hold the soil in place. So there was just massive dust storms. And the dust storms supposedly helped to bring an end to the ice age because the dirty glacial ice absorbed more sunlight and it hastened the melting. It happened to be coincident with the right Milankovitch cycle too, so everything conspired to bring the ice age to an end, but the starvation from CO2 may have played a key role. Too little CO2. Okay, so CO2 is definitely not a pollutant. It's actually very beneficial to life on Earth. And we've been in a famine now for 15 million years, say. Here's what happens if you do laboratory experiments with CO2. This is Sherwood Itzo, a very well-known plant scientist in America from Arizona, and showing the growth of a Mediterranean pine that they used for experiment. And this was the ambient then, which was, you can see some years ago, 385 parts per million. And these are pines grown in different amounts of CO2. They were enclosed in plastic containers here, and this took several years to do this experiment, but you can see the steady increase of growth. I know a number of you have probably seen this before, but there's no doubt that plants do much, much better with more CO2. I should hasten to add that in this case, these pine trees had plenty of water. They got watered every day, so there was no issue of running out of water. They also had a balanced nutrient soil. There was plenty of nitrogen and phosphorus and potassium. If you don't do that, it increases, but it doesn't increase nearly as fast because, plants use up they use up all the nitrogen if you add more CO2 and don't add nitrogen or you don't add potassium. But farmers are not stupid. Farmers always add just the right mix of the key fertilizers so you get the maximum yield that gives you the most money. So if we have more CO2, farmers will simply use a little bit more fertilizer to make up for the fact that the plants are able to grow faster. They already do that in most places. And here's a picture of the greening of the Earth, which is seen from satellites. So since this is data from Australia, and this is how much the greenness of the Earth has changed since between 1982 and 2010. This, by the way, is continuing just inexorably. The Earth just gets greener and greener. And one thing I want to point out is the effects of the greening are most pronounced in arid regions. So here's the southern tip of the Sahara Desert. There's where the greening is maximum. This is the Great American Desert, the western parts of the United States and Canada. Very dramatic greening there. These are dry regions. Western Australia, very dry. Western India, the Ghats here, very. There's a reason for that, which I'm going to talk about in a minute. But the main point is that the only effect you can really attribute to CO2, you can't attribute extreme weather to it, you can't attribute warming to it, but you can attribute the greening. So the one clear effect of CO2 has been a greening of the Earth. And why anyone would think that's a threat to mankind, I don't know, but some do. Yeah. So let's talk about how a plant works. So a plant, take an elm tree. The leaf has got lots of little holes, stomata, that's a Greek word for little mouths. And the stomata are there so that CO2 molecules from the air can bounce around and come into the plant where they're caught by the biochemical machinery of the plant, and with the aid of sunlight are converted into sugar. So one CO2 and one water molecule adds another unit of carbohydrate to a sugar molecule. And the trouble with this is that for every CO2 molecule that comes in, one oxygen goes out. You have to get rid of the waste oxygen. That's good for us. We like the oxygen. But you typically lose 100 water molecules. And that's because the vapor pressure of water in a leaf is typically 100 times greater than the partial pressure of the CO2. So this is a real dilemma. It's a trade-off dilemma for the plant. It has to have the hole to get the CO2 to grow, but the same hole means that it's drying out like crazy because of the loss of water. It doesn't matter much in Holland because there's lots of water in Holland, but it matters a lot in the United States and Australia and India, where you have dry farming, and often it doesn't rain for 2 weeks at a time. That's one problem that's actually solved by more CO2, because the elm tree is not stupid. If you look at an elm tree leaf from a herbarium, in the London herbarium from 1850, and you count the holes in the leaf, it has a lot more holes in the leaf when it was collected in 1850 than it is today. So trees and other plants know that when CO2 increases, they don't need to grow leaves with so many holes in them. And they're more efficient, therefore, with water. They don't need to lose so much water in the process of living. So positive effect, the most important positive effect of CO2 in the wild, like the satellite pictures, is because of the increased water efficiency. Plants can grow at the edges of deserts which would not have supported life 100 years ago. Now, there's another more interesting one, at least to academics. I don't think it's nearly as important, but I will mention it because it's of interest to me, being an academic. And that is that this fixation of carbon dioxide is driven by an enzyme called rubisco. I don't know whether it's marked on here. Yeah, rubisco. You can barely make it out. This is the most abundant protein in the world. If someone asks you what's the most abundant protein, you know the answer now. It's rubisco. And, you look out at the grass that's growing, along the highways. That's all rubisco. It's full of rubisco. Rubisco was invented 3.5 billion years ago when photosynthesis was invented by blue-green algae. And At that time, there was no oxygen in the air. You know, all the oxygen we have today was produced by photosynthesis in plants since 3.5 billion years ago. And so nature made a mistake when it invented Rubisco, because it turns out it's poisoned by oxygen. But that didn't matter at first because there wasn't any oxygen around to poison it. But now there's lots of oxygen, you know, it's 20% oxygen in the air. It's been as high as 30, you know, sometimes in the past, recent past, by geological standards. And so when there's not enough CO2 in the air, which is true today, there's not enough, we really are in a famine, C3 plants like the elm tree, essentially all forest plants and most agricultural plants, will now and then, in fact, 20 to 25% of the time, instead of grabbing a CO2 molecule, they'll grab an oxygen molecule. And instead of making sugar, they make things like hydrogen peroxide, which are as poisonous for the plant as they are for you and me. You're not supposed to drink hydrogen peroxide. So when you buy tea and it says full of antioxidants, the antioxidants are there to deal with this engineering mistake of the Rubisco, that the damn Rubisco makes all sorts of oxidizing products, you know, by mistake. And the plant has to get rid of them as fast as possible before it completely tears up the biochemical machinery in the plant. So that's a real problem for most of our agricultural plants and all of our forests. Now, so in response to that, there's a second photosynthetic path that has developed called the C4 path. And there are a number of very important agricultural crops. One of them is corn, American corn, maize, and the other is sugarcane. And both sugarcane and corn have a different internal structure. They protect the Rubisco, this famous protein I mentioned, inside a bundle of fibers. So the fibers are impermeable to oxygen, so the oxygen can't get in. And they've developed ferry molecules, transfer molecules that capture the CO2 and are able to inject it across this oxygen impermeable barrier into this low oxygen region, the fiber bundle, where you get 100% photosynthesis instead of 70 or 75% in a normal plant. And this comes at some cost, you know. You have to have all this additional machinery to do that. But nevertheless, it increases the efficiency so much, especially in hotter, drier parts of the world, that it's worth doing it. So corn gives us much better yields in the United States than wheat does, or soybeans, you know, which are C3 plants. And largely because of this clever trick that it uses, the C4 trick, the tissue bundle. Okay, so this problem is called photorespiration. And so the other thing that added CO2 is doing is it's suppressing photorespiration, because the more CO2 in the air, the less likely the Rubisco is to make a mistake and get an oxygen instead of a CO2. So a secondary increase in yield has come from the photorespiration suppression. And so one thing that you expect to happen then is that the C3 plants will begin to be more formidable competitors to corn and sugarcane, which are almost untouchable right now because they are so advantageous. But that advantage is slowly being lost as more CO2 is coming into the air. I don't think that's a problem, but some people do. They swear that all weeds are C4 plants, but that's actually not true. All right, so here's Rubisco, by the way. I maybe should have shown this, but what Rubisco is supposed to do is it's supposed to grab a CO2 and a water molecule. They don't show the water here, but it's flooded with water, and add it onto a 3-carbon sugar. But every now and then it gets confused. It can't find a CO2 molecule in time, and it's primed like a battery with ATP and NADH, all the necessary biochemical products, and it takes oxygen and it turns it into toxic products that the plant then has to get rid of. That's why there are antioxidants in the tea leaf. Now let me come back to models, and here I feel like I can speak with some authority because I participated in making one of the first models in 1982 before Al Gore even came along. And so I and my colleagues had estimated that the change in temperature per decade from CO2 would be about 0.2 degrees per decade. And so here's my prediction. The gray bars are all the other predictions since. This was one of the first. And it's interesting, they hover around our initial guess. And I can tell you, since I would say this was essentially a guess. And the red bar is what's observed. Okay, so here are all these predictions made by billions of dollars worth of supercomputers. Ours was actually only made with laptops. But here's what's observed. So, that's really terrible. The warming was less than 1/10 of a degree per decade in this particular period, 1998 to 2012. This was the famous hiatus, the pause. But if you look over a longer time period, it's just as bad. This first one's from 93 to 2012, and that doesn't include the hiatus. But again, you can see the predictions are 2, 3, 4 times larger than reality. But yet we're basing policy not on these red bars, which is what nature is really doing, but on these black bars, which are produced by supercomputers and garish displays on screens with threatening-looking red colors as the Earth boils down. And it's amazing. And this, by the way, is published in Nature. It's sort of the Vatican of climate extremism, but they couldn't avoid publishing it because it's the truth. So here's another comparable view of that from John Christie at University of Alabama, Huntsville. And what I'm showing here is, again, model predictions, an average here for 102 different model runs versus year. And here are observations. So what the Earth is really doing is, as measured by balloons, you launch thousands of balloons every day, and they float up to the stratosphere, and they measure temperature and humidity as they go in the wind direction, radiosondes. And so that's the balloons, and they're warming much, much less than the climate predictions, the model predictions. And the greens are John Christie's specialty is satellite microwave sounder measurements of the same area of the atmosphere, and they agree quite well with balloons, but neither of them agrees with the theories, and yet our politicians are using this red curve rather than the observed curves. It's amazing. Yeah. Now, how do they get such a big? How do they get this so big? It's because they have invented positive feedbacks. So let me try and give you the flavor for that. The way the radiation gets to space, perhaps we'll go back to this Planck picture as quickly as I can here. The only part of this curve where radiation is reaching space from the surface of the Earth is in this narrow region of frequencies here, and this narrow region here. This is called the atmospheric window. So this is where there's very little greenhouse gas absorption. The only problem is this ozone band. That doesn't matter that much. But everywhere else, the radiation is not coming from the ground. It's coming from warm greenhouse gases at higher altitudes. And so CO2, you notice, has very low radiation. It's not because it's absorbed a lot of ground radiation. It's because it's radiating from the stratosphere where it's very cold. And this funny little spike is radiation from the top of the stratosphere where it's actually fairly warm on account of ultraviolet heating. The ultraviolet light gets absorbed by ozone. So this is the very top of the stratosphere. This is lower in the stratosphere. And the edges are at the base of the stratosphere, the upper troposphere. So the way feedback works is they say, this is water vapor radiating at maybe 4 kilometers altitude on average. And they say because of the warming from CO2, the water vapor will move up to 5 kilometers. So this black curve here will move down because the water is trying to radiate from a colder altitude, a higher, colder altitude. So that's the type of feedback that they've invented. That's actually was invented by Manabe, who got this year's Nobel Prize for Physics. It's amazing. But I know Manabe, he's from Princeton. He's a nice guy. And if you talk to him in private, he agrees. He will never publicly agree. So anyway, that's one feedback. The other feedback is clouds. You know, I mentioned earlier that the dominant knob for climate really is clouds. You know, half the Earth is covered with clouds of one type or another, so a little more than half. And the slightest change in clouds is much bigger effect than doubling CO2. And so the second positive feedback mechanism is changes in clouds that amplify the warming from CO2, the direct warming. Now, there's, you know, sort of a philosophical problem with that, because these are all positive feedbacks. You know, you have an effect on a system, and the system responds by having an even bigger response than you started with. So that's positive feedback. But most systems, natural systems that we really understand, the feedback is negative. You know, there are very few natural systems that have positive feedback, and that's actually dignified by a principle. It's called Le Chatelier's principle. This French chemist Le Chatelier. See if I can find him back here. Here he is. So this is the Wikipedia definition of Le Chatelier's principle. It's pretty accurate. When a settled system is disturbed, it will adjust to diminish the change that has been made to it. Okay, and in other words, most feedbacks in nature are negative. And, you know, there are hundreds and hundreds of examples of that, you know, of this negative feedback. But our climate alarmists, they all claim that the feedbacks are positive. Not just a little, hugely positive, almost the limit. You can't get them more positive without the thing tipping, you know, so they like to talk about tipping points. But that's very unusual. There are a few cases like that, but it's not common. And there's no support. The paleoclimate data, I showed you a little bit about paleoclimate. There's no support in the geological record for a positive feedback. In fact, the geology is quite consistent with either no feedback or some negative feedback. One example is the faint young sun paradox, which I think some of you know that 4 billion years ago, soon after the Earth was formed, the sun was quite a bit less intense than it was today, 10, 15, I don't remember the exact figure, but it's of that order. And so if you reduce the sunlight that much with our current climate models, the whole Earth would freeze. You know, it would be a ball of ice. And yet all of the evidence you have from that period, you know, 4 billion years ago, shows that Earth was covered with liquid water even then when the sun was quite a bit dimmer. So the implication is there's something about water on Earth, clouds, water vapor, that fixes the temperature in a fairly narrow band, at least enough to keep liquid water over the Earth most of the time. There have been a few occasions where there's some evidence of a snowball Earth, where the whole Earth was covered with a glacier, but they're few and far between, and there's, I would say, still a little bit controversial. But most of the time, the Earth has liquid water, and that's certainly not consistent with our current climate models. And so my friend Dick Lindzen, for example, has made some suggestions on cloud feedback, which might be able to explain that. You can't explain it with greenhouse gases. It just doesn't work. Okay, so no, people keep asking me, but what about this 97% consensus? You know, how could 97% of scientists be wrong? And the answer is there are plenty of times in history where they've been wrong, even when there was no political force behind them. You know, here's an example: is the theory of continental drift. And the hero there was Alfred Wegener. And he was a German astrophysicist. And he pointed out that if you put South America and Australia and Antarctica together, they fit like a jigsaw puzzle. And even more, if you look at fossils from, 300, 400 million years ago, you see the same fossils here in South America as you see now in Africa here, or same fossils in in Antarctica as South America, and across Africa, and across the southern tip of South America and South Africa. And he was laughed to scorn. And some of the objections were, well, he's an astrophysicist. What does he know about geology? That was particularly bad in America. The Americans were the worst of all at that time. The Europeans they behaved with more honor than the American geologists. So he was just laughed to scorn. And poor guy, he never lived long enough to see himself vindicated. He was not vindicated until the late 1950s, early 1960s, and it came about when the United States Navy finally declassified our magnetic surveys of the North Atlantic, and everybody could see there was this mid-Atlantic ridge with a perfect mirror image spreading, which you could date with magnetic field reversals. And so it was completely obvious that the Atlantic had been spreading quite rapidly, in fact, almost exactly what he had predicted. So poor guy, he fell actually into an ice crevice in Greenland. So he died, with his boots on. I don't know whether they ever recovered his body. But anyway, there are plenty of occasions when an entire field has been dead wrong. And this had no politics in it. And probably many of you are familiar with a more sinister episode, which was Lysenkoism in the Soviet Union. This was biology, where this poorly educated Ukrainian agronomist claimed that he could make apples grow above the Arctic Circle and wheat and simply by breeding and reading Marx and Engels. And this sounded pretty good to the controlling politicians, and so he was heavily supported. But not all Russians agreed with him. A number of them said, well, what about how well the Westerners are doing with hybrid corn and things like that? That fits classical genetics very well. What about Mendel's experiments with peas? And you were lucky if you said that you were only fired from your job. So that was the mildest punishment. Several of the more prominent ones were condemned to death and for questioning Lysenkoism. So it was a really sinister time. And it continued until, it continued well beyond Stalin. Khrushchev was a big supporter of Lysenko. In fact, it's interesting, if you look at Pravda the day after Khrushchev was deposed, the reasons, there were many reasons given by the cabal of people who had deposed Khrushchev, but one of them was he supported the charlatan Lysenko. So I'm just praying that I see something similar like that happen to climate one day. I live to see that. I don't know if I will. All right, well, let me summarize so we can have some discussion. So there are really two takeaway points I want to make, in that the policies are being driven by just crazy computer models. They're obviously wrong, okay? And yet we're still driving policy with stuff that is incorrect. And secondly is that it's clear that more CO2 is benefiting the world. It's a benefit. It doesn't need mitigation, and we should have the courage to do nothing about CO2. We should do things about real pollutants and real problems and not waste money on phantom problems that are making everybody poorer and more miserable. So I'll stop at this point. Thank you.